All right, let's talk about the development of the periodic table. Number 1 says in the warm-up, can you suggest the meaning of the word periodic? Well, periodic is going to mean that there are similar elemental properties recurring on a regular or periodic basis. Number 2, on what basis are the elements arranged in the modern periodic table? Well, they're arranged in order of increasing atomic number. Number 3, what is true about chemical elements that appear in the same vertical column in the table? Well, the vertical columns are known as groups or families, and they have similar properties. Now, let's go on to discovering an elemental order here. In 1817, 52 elements had been discovered, and Johann Dobrinner noticed that there were similarities within certain groups of 3 elements like chlorine, bromine, and iodine, and he called these the triads. And then in 1857, William Oldling proposed that elements could be divided into groups based upon their chemical and physical properties. In 1862, I don't want to butcher his name, but I think I'm going to, Alexandre Emile de Chancourtot, I have never taken French, so don't judge me, arranged the elements by increasing atomic mass. And the elements with similar properties seem to occur at regular intervals. In 1864, John Newland noticed that similar properties seem to repeat every 8th element, similar to the way that the notes on a musical scale are repeating every eighth note. This is known as the law of octaves. Now, the most successful organization of elements was arrived at independently and almost the same time by a German chemist by the name of Meyer and a Russian chemist by the name of Mendeleev. Ultimately, Mendeleev was awarded all of the credit, and I'll tell you, or the majority of the credit, and I'll tell you why in a second. But in 1869, Mendeleev had arranged the elements into a periodic table, and he proposed something called the periodic law. Let's turn the page. He said that if elements were arranged in order of increasing atomic mass, then a pattern could be seen in which similar properties recur on a regular or periodic basis. So Mendeleev's work was published a year before Meyer's, and so Mendeleev chose to concentrate on chemical properties of the elements. And what he did was he left some blank spaces on his periodic table where he predicted undiscovered elements would eventually be placed. And he was correct. And if you take a look underneath here, this is his periodic table that he proposed. And you'll notice that there are blank spaces with lines for elements that weren't yet discovered. And if you take a look at the next page here, there are some of the predicted and observed properties of the element germanium, just to convey how accurate his periodic table was. He also corrected the atomic masses of beryllium, indium, and uranium. So if you take a look at the quick check here, it says who was the first person, oops, I went a little too far. Who was the first person to arrange the chemical elements into groups? Well, that was Olding. Did I misspell it? No, yes, I did. That was William Olding. Number 2, how did Newland's analogy to music apply to elemental properties? Well, similar properties repeat each 8th element like notes on a musical scale. Number 3, how did blank spaces in Mendeleev's periodic table help it eventually gain acceptance? Well, those blank spaces predicted the properties that elements would possess when discovered. And once they were discovered, those predictions turned out to be extremely accurate. Okay, let's talk about the modern periodic table. In 1913, Henry Moseley combined with the discovery of isotopes resulted in the elements of the periodic table being reordered according to their atomic numbers rather than their atomic masses. When the elements are arranged in order of increasing atomic number, there's a pattern that can be seen with similar properties recurring on a regular basis. So with the inclusion of element 117 in April of 2010, the table includes 118 elements, 92 of which occur naturally, and they are arranged in order of increasing atomic number. Elements 113 to 118 have not yet been assigned permanent names. If we turn to the next page, the horizontal rows on the periodic table are known as periods, and they are numbered from the top down, one down to 7. And then the vertical columns are called families or groups, and those are labeled using 2 different schemes. There's an older system which assigns a column a number 1 through 8 with the letters A or B next to them. And if it has a letter A above its group with a number, that means it's a main group or representative element. If it has a B, that means it's a transition element. You may also see those numbers represented as Roman numerals. And then there is the newer system adopted by the IUPAC, which is the International Union of Pure and Applied Chemistry, which uses the numbers 1 through 18, and there are no letters. So we're going to be using the IUPAC numbering system. And there are 2 important things to know about the periodic table. Number 1, elements that are in the same family have similar chemical properties because they have similar outer electron configurations. And then as you move down a family or across a period, there will be regular changes in properties that we call periodic trends, and I'll talk more about those periodic trends in a second. Let's move on to this periodic table here. Here you will see they have labeled the representative elements. Those are groups 1 and 2, where it says representative elements. and 13 through 18 here. Okay? Now, if they are, actually, that goes down to here. The transition elements are everything in between. Those would be 3 through 12. And then the inner transition elements are these inner two rows that fit up in here within the transition elements in the 6th and 7th period. Okay? There is a staircase on the right-hand side of the periodic table. It is this darkened region here. And this darkened staircase is separating the metals from the nonmetals. So you have your nonmetals on the right-hand side, except for hydrogen, which is over here on the left. And then all of the other elements to the left of the darkened staircase would be considered metals. Now, some of the properties of metals are listed on the next page. They are solids at room temperature, except for mercury. They are generally shiny or lustrous. They are good conductors of heat and electricity. They are malleable, which means I can pound them into thin sheets. Ductile, which means I can draw them into thin wires. Flexible, during chemical changes, they give up electrons and they form cations. The nonmetals tend to have properties such as they are brittle solids at room temperature, except for liquid bromine. They are gases usually, or some of them are gases. Solid nonmetals range in appearance from dull or lustrous and translucent to opaque. They're poor conductors of heat and electricity, and they gain electrons during chemical reactions. They form anions, and they share electrons with other nonmetals. Now, something to note is that along this darkened staircase, you're going to have something called the metalloids. Now, the metalloids are also called semimetals. Those are boron and silicon and germanium and arsenic, antimony, tellurium, and polonium. These solid elements are semiconductors, which means they are poor electrical conductors at room temperature, but as the temperature increases, they become better conductors. This is opposite of how metal conductivity varies with temperature, because metals actually become less conductive as temperature increases. Now, as you move to the right, away from the metals, so as you move in this direction across the periodic table, you become less metallic, which makes sense because you're moving away from the metals. So metallic character is one of the trends on the periodic table. You could also say that metallic character increases to the left and down. Let's take a look at the quick check on the next page. It says fill in the missing spaces in the table below. So Si is silicon. Its group number is 14. Its period number is 3. It is a metalloid. Osmium is Os. Its group number is 8. Its period number is 6. It is a metal. The group number 6 that has a period number of 4, that element symbol here is chromium. It is a metal. Mt, Metherium, group number 9, period number 7. It is also a metal. Antimony, Sb, group 15, period number 5. Group number 17, period number 5. Iodine is a capital I, and this is a nonmetal. Now, if we were to rearrange the elements listed here from least metallic to most metallic, we would start with fluorine, then oxygen, sulfur, aluminum, gallium, chromium, zirconium, and then cesium, because metallic character is going to increase to the left and down. So the most metallic will be on the bottom left of the periodic table, and the least metallic will be in the upper right. The letter B. Based on your answer to A above, which of the 8 elements would you expect to have the greatest tendency to gain an electron? Well, that would be fluorine, because nonmetals gain electrons and form anions. Which one has the greatest tendency to lose an electron? That would be a metal, because metals prefer to lose their valence electrons and form cations, so that would be cesium. Let's go on to the next page. Now, the outermost electrons that participate in bonding are known as valence electrons. And the valence electrons are influencing, the number of valence electrons are influencing a lot of things. So let's start by talking about the group 1 alkali metals. So the alkali metals are on the far left side of the periodic table. This group includes lithium and sodium, potassium, rubidium, and cesium, francium, and francium is rare and it's radioactive. These are soft, silvery solids, and they are the most reactive of all of the metals. That is very important to know. The oxide compounds, that means when you have a alkali metal combining with oxygen. When they dissolve in water, you're going to get a very strong basic solution. These metals corrode in the air. They form a dull gray appearance. They react vigorously with water. They produce hydrogen gas during that reaction, and they will readily form compounds with nonmetals. All of these metals have one valence electron in their outermost shell. You can see it emphasized here in this table. That's why they readily lose one electron to form +1 cations, because they become more stable and they become a noble gas configuration. Now, let's take a look at group 2, the alkaline earth metals. These are silver-colored reactive metals. They are not as reactive as the alkali metals. They will readily form compounds with nonmetals. And they're oxides, meaning when you have a group 2 metal combining with oxygen, their oxides are also alkaline, but unlike alkali compounds, some group 2 compounds have low solubility in water. They all have 2 valence electrons, and they will readily form a +2 cation because they want to lose those 2 valence electrons to achieve a noble gas configuration, which is more stable. They would call this isoelectronic, which means that you would have the same electron configuration as the nearest noble gas. Let's take a look at group 17, the halogens. The halogens are the most reactive elements on the periodic table, and they have all 3 of the states of matter represented. And at room temperature, fluorine and chlorine are gases, bromine is a liquid, and iodine is a very rare, and then you have iodine as a solid, and then astatine, which is a rare radioactive element, also as a solid. The elemental halogens exist as diatomic molecules. They will readily form compounds with metals, and hydrogen and carbon and other nonmetals. They have 7 valence electrons in their outermost shell, and they will gain an electron to form a -1 charge. And they do this when they react with metals, and they will achieve their noble gas electron configuration, which makes them stable when they accept that 1 valence electron. And when they react with nonmetals, they share their valence electrons. Let's go on to the noble gases. This is group 18. The noble gases are generally unreactive. Compounds have been made with some of the noble gases, however, and all of the noble gases except helium have completely filled S&P sublevels, And that means that they have 8 valence electrons in their outermost shell. We say that this is a stable octet, and that explains why they have such low reactivity. And if you take a look at the next page, you'll notice that when ions of certain elements form, those ions tend to have the same electron configuration as their nearest noble gas, and that is what makes them stable. Okay? Let's move on to the transition elements. The transition elements include groups 3 through 12, and these are metals, and most of them are hard solids with really high melting and boiling points. And they form cations with multiple charges. And then those cations have the ability to form complex ions. And a lot of transition metal compounds have distinct and recognizable colors, mainly because the last electrons added for the transition metals are put in the inner d orbitals, and those orbitals are closer to the nucleus, and that's how we get those distinct and recognizable colors. Let's take a look at the quick check. Number 1, identify the family number and name to which each of the following properties best apply. Reactive nonmetals possessing 7 valence electrons. That's family number 17, and that family name are the halogens. Remember, the families are the groups or the columns. B, reactive solids that form +2 cations during reactions would be family number 2. These are known as the alkaline earth metals. C, invisible gases that are almost totally unreactive. Family 18, these are the noble gases. D, soft, very reactive silvery solids with a valence electron. That's group number 1, and these are the alkali metals. Number 2, elements in the same family demonstrate similar chemical behavior. Consider the following chemical formulas. Write chemical formulas for sodium iodide, that's NaI, barium sulfide, that's BAS, gallium chloride, GaCl3. Gallium on the periodic table is underneath aluminum, and it has an assigned charge of +3, if you want to make a note of that if you haven't already. Number 2, rubidium sulfide is Rb2s. Letter E, magnesium phosphide, is Mg3P2. Letter F, hydrogen selenide, is H2Se. Number 3, which 2 families contain the most reactive elements? This would be the halogens and the alkali metals. And why is that? That's because they are within 1 electron of being isoelectronic, meaning having the same electron configuration with the nearest noble gas. So they will readily gain or lose an electron. So for instance, the halogens will readily gain an electron. The alkaline metals will readily lose 1 electron to achieve that electron arrangement, which makes them stable. Let's move on to the quantum mechanical view of the periodic table. There are 3 different aspects of the elements in the periodic table, and chemical families are separated into 4 main blocks. If you look here, the first 2 groups, this is known as the S block. The P block are groups 13 through 18. The D block are 3 through 12. And then the F block are the intertransition elements that are the two detached rows underneath. You will notice that these numbers along the top, the 1 through 18, are the more current numbering system, and then the 1A, 2A, 3B, all the way across to 8A, where the noble gases are, that's the older numbering system. And then each block corresponds to one of the 4 electron sublevels, right? So the S, P, D, and F sublevels. And the number of columns or the families in each block matches the number of electrons that occupy that sublevel. So for instance, I can hold 1, 2 electrons in the S's. I can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. In the D's, I can hold 1, 2, 3, 4, 5, 6 electrons. In the P's, you can hold 14 electrons. In the F's. Also, if you read the sublevels from left to right, we follow the order of filling sublevels specified by the Aufbau principle. Once you reach the noble gases at the end, that's when you move down and begin a new period, just like if you're reading from left to right. And each new period specifies the value of the next energy level. For instance, here, this is starting with this 1s, this is where your n equals 1 is usually over here. This is your n equals 2, that's where 2s is. N equals 3 is where 3s is. N equals 4, 5, 6, 7, and so on. And then every new period represents a larger cloud or electron shell where the electrons are spending most of their time further from the nucleus. So the electrons in n equals 1 are closest to the nucleus. The electrons in n equals 7 are furthest from the nucleus. And then if you take a look at the next page, here, this is showing the extended form of the periodic table with the F block, the lanthanides and the actinides inserted after barium and radium. And you'll notice that there's a connection between the electron configuration and the element in the periodic table. And this arrangement of elements was in place before the development of the quantum mechanical model of the atom. And we're just going to leave it at that.